Responsible AI. And this session will be chaired by Professor Eduard Hovy, who is the director of this building, who is the boss of the building. He is the director and he's a professor of computer science, a natural language processing professor, and also the director of this wonderful thing that is Melbourne Connect. I just want to say my heartfelt thanks for him coming along to run this session, because I know how busy he is, and Ed is very, very busy, but whenever I ask him to come and give a talk, he turns up.
Oh, Jeannie. Thank you, Jeannie. Jeannie is one of the best colleagues you can ever hope to have. And anybody who's ever run a meeting with Jeannie will know this. And I think from the last few days you've seen, if Jeannie gives you an invitation, you go, because it's a lot of fun. So thank you for coming. I know that it's close to lunch, and I know we're running a bit late, so we'll make this short and sweet. So Jeannie asked us, can we come and give a little bit of insight, not technical, about what's happening from the technical side when you talk about a responsible or authenticated or believable or trustworthy AI. So I thought, who can I invite? And I invited my 4 colleagues here from the University of Melbourne, I'll introduce them in a second, to come and tell about what different aspects of what this means to do trustworthy AI or responsible AI. And it's actually quite an interesting topic. Now, what struck me when I was listening to the talks from the last 2.5 days, I popped in and out, was a strong dichotomy between what people are saying. On the one hand, we say, not everybody has access to generative AI, and that's a bad thing. We need to make everybody have electricity, and we need to give it so everybody can use AI. Because it's, we need to teach people how to use it, etc. It's a valuable commodity, it's a valuable thing to do. On the other hand, AI is dangerous, and it's going to destroy humanity. And there's these ugly people with a lot of money who go and do all kinds of nefarious things, and so maybe we shouldn't do AI. And so I'm sitting here thinking, should we? Or shouldn't we? Where are we? What's our stance on this? And sometimes we say one thing and sometimes we say the other. And it's an interesting thing to think more from the tech point of view. It's like, what are people in the tech who are not so concerned with the kinds of issues that have been discussed here? What are they doing to try to make the AI trustworthy? If I design a car, if you design a car, and the car is wonderful and great and super, but occasionally it drives off the road and it crashes, you don't sell your car. I'm sorry, right? Unfortunately, thanks to OpenAI and other pushes, people have now bought this LLM car, but the technologists don't quite understand exactly how it works, as I'll describe in a moment. And so it's a very risky position to be in as a technologist, to say, here's all this stuff, and people want to use it, and they talk about it, and they talk about its dangers, and when they come to you and they say, fix this thing, stop it from hallucinating, clean the bias out, don't let it leak IP, and you say, I'm sorry, I don't really know how. But I do know something, and this panel is about the things we do know. So that, without further ado, this is the preamble. How can we ensure that the results of AI processing are responsible and trustworthy? And what has been done, as you know, is people have done training and fine-tuning to try to move away from problematic topics and areas. OpenAI did this whole program of open human reinforcement feedback learning, where they paid people in Kenya $2.10 US a day to go and vote up and down so that they could feed back the down into ChatGPT, so that they created a list of stigma words, essentially, or stigma tokens, so that the machine would prefer, when it's re-ranking, to not say bad things and say good things. But as we all know through jailbreaking, that doesn't work so well. I have one of my students is working on this topic, and I saw a heat map yesterday that showed that when you approach either the commercial systems or the non-commercial systems and you try to jailbreak them, they have been trained to be very careful when you jailbreak them on personal topics like ideational, like suicide and so forth. But when you ask them how to make bombs and how to derail trains and things, they're quite happy to tell you. You just do a few little tricks and they'll tell you those kinds of things. So there is a lot of work to be done on human reinforcement, feedback learning, and so on. The best engine, by the way, if you want to know, is, of course, Anthropic. It's the best in everything. When it discovers that you're trying to jailbreak it, my students, the whole message, it comes up with a message in bold saying, "You are trying to jailbreak me. I am hereby terminating the conversation," and it kills your window. It kills your window. It doesn't just stop, it kills the window. So that's actually a very good thing. I love Anthropic because that's the right way to respond to anyone who tries to jailbreak them. So that's what's happening there. So you can also have, like Grok does, for instance, two-level architectures where you do something and then a second LLM looks at the output of the first and then sort of judges it for acceptability and so on. But all of this, none of this is actually good enough for what a real human being wants. So here's the panel. I would like to describe, listen in 5-7 minutes, something about explanation, what explanation really is, because explanation is a big part of trust. When I go to the doctor and the doctor tells me something I don't know, I have to trust. And when the doctor explains to me in the doctor's way, I trust more. I think we're going to be in that position for a long time with respect to AI. It's going to tell us things that we don't know and we have to trust. And if it can tell us things in ways that we accept, we will trust more. We may not be completely convinced, right? Then Sarah will describe AI safety by design. What has been done and how could you actually go into the machine and design it to be safe? And she'll tell you just a little bit in a non-technical way what that means. Caren will talk about validation across modalities. What happens when you see something in one medium, like text, and you see something in another medium, like images, and if you're not quite sure what is true or not, maybe one image can help you convince or find problems from one modality can find from the other modality. So that's a good way of actually helping to cross-correlate statements from an LLM that you may or may not be sure that you believe. And then Tom has built some small LLMs himself on his laptop, very tiny ones, not big ones, but he's built them. So he's going to tell us about what you can do when you have a small LLM to just do sort of simulations or trials and things just to see how you can trust, where your trust breaks down. You can sort of play with that. Those are the 4 themes that we're going to describe today. That's okay? And we'll do so fairly expeditiously, and then we can have a little question and answer afterwards, then we go for lunch. So let me tell you first, just 4 or 5 minutes about explanation in AI. One has to start, I think, with what trustworthy actually means. What does it mean to be trustworthy? If you say it means without error, then you're unrealistic. AI is not magic. No human is magic. Everyone makes mistakes, and you can expect an AI to make mistakes too. The superhuman AI fallacy, where you expect AI to never make any mistake, to never do anything wrong, is just crazy. It's not going to happen. It's just not going to happen. Like everything else, AI will make mistakes, and AI may, in fact, kill people at some point. Every technology does. So trustworthy cannot mean has no mistakes. In practice, in reality, when you use AI, you will have to accept that there are some mistakes. But you want to still have trust, right? So maybe trustworthy means the AI did the right thing, starting with the knowledge it has. That's better. That means I can go check what it started with, and I can check, did it do the right thing? But I have to sort of understand what right means, right? So then one could say, well, maybe trustworthy means the AI did what I would have done, starting with the same knowledge and having the same goals. To me, that's a much, much more sensible and understandable kind of definition, which one can then proceed with in legal and other terms, governmental kinds of terms, because you can sort of relativize it based on where it's starting from. And if the AI starts from an inferior place or an inadequate place or an uninformed place, you can just say that's why. Or if it's reasoning wrongly, you can say that's why, right? So you have to start looking then at different parts, different aspects of what the AI is action is, and then you can check each of them in a more sort of sophisticated and informed way. So we need to confirm the starting knowledge. What does it start with? What does it know? You don't expect the same from a child as you expect from an expert, right? You cannot expect the same from an LLM that's a small one, from an LLM that's a big one, from a human. You need to understand some of that. You have to understand the goals. What was it trying to do? It may have tried to do something completely different, which in fact might have been correct for it, just you didn't understand its goals. So one has to understand what are its goals, and one has to then understand its reasoning. And AI has, over the last 25, 30 years, looked at each of these aspects, and that is in fact, I think, what an explanation is. Most AI explanations focus just on one aspect or another, but a true explanation, if you think about it, has all these aspects in. So a typical explanation in AI, if you look at it, if I ask you, why do you attend this conference? Why do you attend this conference? Think of your answer in your mind and keep it there, right? Would you say, as an AI system would say, because 86.7% of the time, when the following conditions are true, then I attend a conference. There's AI or learning in the title, and the conference is not too far from my home, or someone invited me, and the conference has people from this and that, and the conference is less than 5 days long, etc. Is that how you reason? Honestly? Would that explanation satisfy you? I don't think so. What that is model interpretation. It's telling you what the model is doing. It's not an explanation that you as a human understand, and ultimately we're not interested in what the model does. We're talking to society, and we have to make sure that the explanations that are given to society are couched in terms that society accepts. So we have to look elsewhere, I think. So let's look at then the different pieces. To confirm the starting knowledge, you can go and do something like this. You can prompt for the facts used, and there are all kinds of techniques for putting little probes into an LLM and pulling out the knowledge that they have. There's something called hotspot analysis, which you might know, where you look at the transformer architecture, you look at the neurons, you look at the embeddings, the little encodings of the words that you have, and you look which are high activity and which are low activity, and you can sort of infer roughly for this particular task, these were the aspects, the topics, the facets, the words that were important to the machine when it came. These are the things it banked on, these are the things that it used. It's sort of an indication, a weak indication of what the machine started with, what it knew in some sense, right? You can probe the network in different kinds of ways. So there's a little picture on the bottom left of what sort of an embedding hotspot analysis looks like. You don't have to worry about that. It just means that you can go look at the innards, at the brain of this thing, and you can just see where's the high activation, where's the big numbers. And then when you can translate them back into English, you can sort of see what kinds of words somehow were relevant or accepted or used in this explanation or in this task that you gave it. So that's a little piece. Now, you also have to confirm the goals, and most AI doesn't worry about confirming the goals of the system. Now, I put there Maslow's hierarchy, the little hierarchy that we all accept. Some work that I did with a student a long time ago, we used a much bigger taxonomy of goals, this thing here, which was built over a period of a decade by psychologists in Los Angeles. And so, to them, if I ask, why do you attend the conference in terms of goal language, you'd say, because my goal is to learn about the topic. Or because my goal is to meet these and these people, or to see this in this place. To me, that's a much more natural, convincing explanation than the previous one I gave. When I speak to an AI, I want this as well as I want the hotspot analysis. I want this too. I want to know what's the goal. Now, an AI doesn't know a goal without being taught, right? So one has to put in this kind of taxonomization, this kind of analysis of what are the human goals, the humanly acceptable goals, the legally acceptable goals, and then one can do what we did, for instance, in this project with the student there, a classifier. For instance, you can ask, why do you like this restaurant? And you get a sentence, well, everything is always cooked to perfection, and the service is fast, so we have positive cooking and positive service. And when you do a little classifier, you see, oh, we're talking about self-fulfillment, this goal here, and we're talking about appreciating beauty, this goal here. And if you say, well, while the ambience and atmosphere were great, the waiter was rude at times and not very friendly. So we have a positive and negative. So again, we can appreciate beauty, and we can look at there, whatever this, avoid conflict or something. You have to develop your taxonomy of goals in such a way that it responds to the organization, the society you're talking to, the legal framework you're working in, and then you must make your AI speak to those goals so that you can properly explain what the AI is doing and why it's doing to the user. And thirdly, you have to look at the reasoning process. If you know what it's starting with and what it's trying to do, you have to look at how it gets there. Now, this is a notoriously difficult thing in LLMs in AI. And so in the last year or so, 12, 13 months, an area called mechanistic interpretation has risen, and I think that's one of the two most important areas in AI research. To do mechanistic interpretation, you look at the actual network, the transformer architecture with all the neurons, and you look at the flow of the activation numbers from layer to layer, from word to word, as you go left to right, and you look at where the attention moves and how it combines. If you want to then give an explanation, say, I know how this thing thinks, to prove that you know how this thing thinks, you must be able to predict what it's going to think next, and you must be able to change so that it thinks something differently. If somebody says to you, I want you to change it to think, you've got to make it think differently. So that's what people have been doing, and I have a group here, a very active group. We've been doing that sort of work too. There was something called circuits that people have sort of defined a little while ago. They call this thing circuits. There's been a lot of work with Anthropic. Here's a picture of a sentence that we ran in the sort of Anthropic circuit model. In the sentence, in the hotel laundry, Emma burned Mary's shirt. So the manager scolded. Who do you think the manager scolded? Did the manager scold her, him, Emma, or Mary? And when you trace the circuits, here is the different layers up and down from the neural network, starting in the bottom, going up. Here's the words, in the hotel room, Emma burned Mary's shirt, so the manager scolded. What's my next word? What am I going to say next? You can look at this little graph of the high activation nodes, and you can sort of draw a little picture to say, this prediction is going to rank the words that come out in this order. And you can sort of trace why. You can look at the numbers. You can begin to understand what's the internal logic of the reasoning. It's a very difficult thing to do. It doesn't work very well. So we've developed a new method to do that. And we're busy writing some papers on this, which identifies relevant concepts by a contrastive analysis method and constructs what's called a steering vector. That's a vector that a little mathematical operator that you put on the network, and that pushes your reasoning into the place you want it to push. So you can make it think something different. And one of our experiments is to change the gender bias. You ask any LLM in the world, it'll tell you that nurses are women. It'll just say, you put a sentence in with nurse, it'll say her, it'll say she. We want to make it think that nurses are men. We build a steering vector that looks at gender, except when the person is pregnant, and moves the gender, in the context of nurses, from being woman to being man. So you input, the nurse helped the patients, so they praised, it would say her, but after we apply this little steering vector, it says him. And it says so for any kind of sentence that you want. So we prove by doing this that we can actually control the way the reasoning works. We understand what the anchoring concepts are and where we want to go. That's part of understanding how reasoning works, right? If you can see how somebody is thinking and you can change their brain so that they think differently, you sort of understand how they're thinking. That's the goal here. And so there's a little bit more details about this. So I think explanation, in conclusion, explanation in AI is when an agent explains its behavior, you have to trust the knowledge it starts from, so it's got to tell you that somehow, maybe hotspot analysis or something better, probing. You have to understand why it's doing what it's trying to do, so you have to have the goals, and you have to understand the reasoning. How did it get to where it got? It's got to be able to explain those three things to you. Then, if it's couched in terms you understand at the level of detail you need, then the explanation is convincing. It's a sociological dialogue operation. It's not a logic operation, right? So it's a very difficult, complicated thing to build good explanations, but AI people are working on this, and one can hope, I hope, that in a few years' time, AIs will be more able to explain their reasoning to you in ways that you accept, and not just a sort of simplistic little phrase, but actually when you probe it and you say, where do you start from? What's your goal? Why do you do this? It can actually do so in a way that you can then say, well, it may have made a mistake, but like a human, it has its reasons. I can sort of judge them on the reasons. Okay, that's my part. And now maybe Sarah, could you come next for the next piece?
So I'm going to give you a very quick few minutes insight to what are the vulnerabilities of current AI systems and why implementing or integrating safety guardrails into these models is a good idea. So let's start by defining what do we mean by trustworthy AI from more technical perspective. So Ed gives you a definition from more like general perspective, but what AI developers define trustworthy AI. So an AI model is the one, a trustworthy AI model is the one that can understand and communicate its uncertainty, can tell you, I don't know. That would be fantastic. So we can see that more recent systems like ChatGPT say, I don't know, but that's a very fancy new thing that is happening, and it doesn't use it as often as it should, unfortunately. It hallucinates a lot and gives you wrong answers. It should be adapt without forgetting, meaning that if you are applying it to a new environment, for example, we have designed a model in Canada, now using it in Australia, and it sees a kangaroo, we should be able to adapt it and understand this is a new environment without forgetting black bear that is in Canada. It should be able to resist to manipulation and when you have an adversary who wants to change the model or our data. It should be able to prove its correctness. So this goes to explainability, not only explain, but it should say, I can prove it to you that I'm correct, and provide a legitimate explanation and outcome. So that's the ideal, that's the goal, but we are far from here, unfortunately. The problem is that our AI models, our fantastic AI models, are not as smart as we think they are. Our beloved ChatGPT is really biased, it hallucinates. For example, in an experiment, they ask the model to write a poem about Trump. It refused, but it had no difficulties writing a poem about Biden. You can wear this T-shirt with a simple print, then you become invisible to security cameras, like wearing an invisible cloak. Alexa played loud music in the middle of the night when the neighbors even had to call for police. Kid-friendly robots hurt kids many occasions. Our AI systems are not doing well in terms of security and defense. Our cybersecurity attacks are increasing every year. For example, a couple of years, it increased by 38%. This is an interesting one. At the bottom, an artist decided to fill a trolley with a few dozen of mobile phone and walking up and down Google office in Berlin. And you can see an empty street, it shows heavy traffic. So even you can fool Google Maps without knowing much about how it works. So an artist with art background can also fool our system. It's not that difficult. You can put a sticky points or a spray road signs. I should stand here, I guess. Road signs and fool our fancy, expensive self-driving cars. So, what is the challenge? Why AI is failing so much in very simple day-to-day tasks? The problem is that they're not robust to changes in the environment. They don't know how to deal with kangaroo if they haven't seen it before. They can be easily manipulated. You don't need to have technical understanding of machine learning and how do they work or how they should generate it. You can manipulate them and you can fool them. And the other issue is that they're really overconfident. You've probably experienced when you work with, for example, ChatGPT again, and talking about something completely fictitious. With high confidence, it answers you without really doubting its answers. To give you some idea what's happening, like here we have example of frog on the top left. I promise this is the only graph I'm gonna show you today. So on the top left, we have an image of a frog, and we keep adding more and more noise to it to the right that is basically not really clear or visible. And we can see that as we increase the amount of noise, the accuracy of the model drops. It starts giving you wrong answers, but the confidence of the model increases. So you're giving a poor quality data to the model, it comes with the wrong answer with higher even confidence. So what's happening? Why we experience this? The reason is that when we are developing AI models, we think we know most of the things. We think we are in this beautiful glass house and everything is almost clear. So, and based on that, we are going to design a model and optimize a model that gives us the highest accuracy for this setting. And say, okay, if something goes wrong, we have some post hoc solutions that can mitigate any problem. But the thing is that real world is highly chaotic. There are lots of uncertainties, changes. We don't know what's really happening in the real world. And to be able to mitigate this challenge, we need to understand how our system is working. And instead of having post hoc fixes, try to understand the internal mental model of our AI system. Try to understand how it changes, how it's reacting, and when it's uncertain about the outcome. One way to do that is looking at the interaction between different layers, understand which part of the network is making the decision. This is what also Ed mentioned about the explainability. So not only explains, but if by looking at this change, by looking at these connections, we can figure out whether the model is doing what it should do. So for example, on the left, we have an example of a model that trained on a correct data set. And you can see it uses the red lines show the layers or the nodes that are used in decision making. And you can see most of the layers are used in the decision making. But on the right, we have a bunch of models that are backdoored. We had an adversary change the input to an inserted trigger to take a specific action when this trigger appeared. So when the model is manipulated, we can see that the model is not using the whole model. It's using a part of model. Tends to use like later layers toward the right. So this is an example of understanding a change in model behavior. So in this way, it's like our model is behaving abnormally, so something is suspicious. Another way is to look inside the model and understand the patterns that the model learned. Try to, for example, use statistical properties of these patterns, like intrinsic dimensionality, curvature, and so on. And by capturing that, we can understand that sometimes the model can separate this statistical result, can separate unusual patterns, or like manipulation, backdoors, adversarial samples, from what is clean. So here in this example, the green samples are clean samples, are not manipulated, and the red one is the one that is manipulated. And by looking at these statistical properties, we can see it's very, very different from the blue samples. So these are some approaches to understanding models, to understand model behavior. And in this way, we can integrate our guardrail into the model and prevent the model to generate inappropriate or inaccurate results. So what are the advantages of safety by design compared to existing solution is that we come up with a model that has safety built in the model. It's a proactive rather than reactive solution. It requires less human interaction or oversight. It's more robust to changes and shift. It's auditable, so it can generate explanation, and also as individuals, as a technical person, we can go and see and try understand what's happening. And it's much lightweight. We don't need to have heavy computational intensive solutions. Thank you. I know this was very technical. I'm happy to explain more in the question and answer section. Thank you.
Oh? Okay. Oh. Okay. Yeah. All right. The reason why I actually use this, I need to actually use the audio, my machine. So just want to double check. Yeah. So. I'm actually doing the multimodality. My name is Caren, and I just really want to share something like a good example to show. So I want to actually go through about like from the accuracy to selective attention. So multimodality, trustworthy, AI validation. If there is, that'll be really wonderful. Unfortunately, there's nothing so far. I'm very sorry, but I want to show that how we can do that in the future. So firstly, I want to show that we have this like video. I'll show this like video only. There's no audio. Try to guess what is this like emotion. What do you think so? Sorry? Sad. Any other? Frustrated. Frustrated. Like you need to choose one of them. For example, yes. Any of them?
It may be angry.
Angry. Yeah. And then what about this? What if I just like really play the audio only? Is okay. Disgust? Yeah? Fear? Sad? So then what we actually did is like asking the evaluators and multimodal AI both, what do you think when we just listen this audio only? And it actually comes out with the fear. But the difference here is, like, what if I show this one together with the vision and audio together? Like this, it comes out with sad. So both of them, actually human and multimodal AI, actually really found that as sad. This is a really, the data set named CREMA-D. You can actually download it and double check it. It's actually very interesting to see that the point is, the actor actually was asked to act fear. But when they just really looking at this video and the audio at the same time, they found this sad. But when they listen only the audio, they found it fear. So then like you may just say that, so what is exactly the answer? The answer is not that important. The point is, in order to find out which one like multimodality, use this multimodality efficiently and smartly, you need to find out, select which modality and features are important. Some of the tasks you may found that like vision and audio may be important together, but some of the cases you found that audio only may be important. The problem is, There's nothing like that. There's so many multimodal LLM actually coming out. Even the GPT, they just trying to make it up like multimodal LLM. Everything is multimodal these days. They just trying to ask you to put this video, image, audio, or they can just put it like everywhere. Every month, not every month, like every week, there are new types of version of this multimodal LLM actually keep coming up. The point is this, what they really focus on now is based on the pre-training, because whole thing, like the way we have this multimodal language model, we normally have the pre-training big data, and then that actually data come from just like a coarse-grained image text. So which is, how do you actually get the image and text aligned data always? The website or the web. But the problem is, as you know that, there are so many things like images available, but it's very difficult to find out this relevant text caption all the time. So that's why they just focus on that, like how we just trying to get this image and relevant caption all the time. But the point is, yes, we have this alignment now, but you don't really understand which is actually important in different types of tasks. And the same thing, 2023 and 2024, they found that we actually have now really high quality caption, long caption using GPT. So they just generate this image caption now to GPT, and they just found that we got so many data, the large data to train this LLM. But still the same, they just focus on alignment only. Same as the video and text. So normally when you have this YouTube, you have YouTube text description and the YouTube video at the same time. You just try to train it at the same time together and just focus on the alignment. This is the architecture of this multimodal LLM. To be honest, majority of the multimodal LLM actually trying to train like this. I drew this figure myself, but each of them, they can see that like the input is like image, video, audio, or even like time series or any kind of sensor data, whatever you actually put as the input. You need to have this like a modality-based encoder, or you may have like unified encoder, but it's not really working as always. So they just trying to make this modality-based encoder, each of them, like visual encoder, audio encoder, or unified based. But eventually what they really want to do is just focus on these like projector, how they make this alignment. So they just trying to find out whether this video is aligning with the text or not. They just focus on this one. The point is, this is like, they know that those are related, but they don't really focus on which one is important in each task at all. So, and it's very difficult to modify that now, which one to focus and which one to ignore, exactly what happens. So the reason why it actually happened is multimodal LLM architecture challenges. It depends on like pre-trained backbone. Of course, like Google or OpenAI or the big company can just try to just make this training, the big models easily, the pre-trained backbones. But majority of us, we cannot really pre-train it like easily like that. We don't have data or there's resource as well. And that's why we use this like thing, pre-trained backbones and frozen it and trying to test it and tweaking a little bit about these understanding part, that's all. The other reason is limited flexibility. Because we're using this pre-trained model or the big size of the model, and the data set is always like the text and image together, which is aligned caption and image or video. So that's why it's very limited flexibility to train something to better than image and text only. There is audio or sensor data. There's so many other modalities in the world that you can see now even, you can feel it, you can have like smelling, right? You cannot really collect this data easily. So it's very difficult to just involving this modality and then selecting this modality in different types of tasks. Third is evaluation and consistency across the modality. This is exactly the thing that I actually mentioned, this evaluation metrics and method is really none. So you can see like each of the task-based evaluation, but you cannot really tell that this multimodal LLM is really working well. How can you say that GPT is working well, better than Gemini, for example, or vice versa? And deciding how difficult a different modality can contribute to the output in the end is very challenging, and particularly dynamic scenarios. So they're really preliminary stage of updating this knowledge now, like how to update these knowledge in LMM. But in the future, it's not just randomly updating the knowledge, but you need to actually see that what kind of tasks, as you can see, like emotion detection. Do we really need to use like the video and the audio together, or just focusing on the audio only? So you were just trying to find out when you select these selective attention to see the modality-based understanding. So we have this prompt engineering or fine-tuning in the instruction, or prompt vision fine-tuning, or even human feedback now. So how we just trying to handle these kind of thing in the future will be the point. Okay, thanks for listening. It's like I just tried to make it like Gemini with trying to use multimodality and GPT and WISC, but yeah, you would just see like which one is working well. Thank you.
Okay, thanks, Ed. Okay, hi everyone, I'm Tom. I'll try to encourage a bit more audience participation in this one. This is the only Genie joke that I know that is appropriate for the workplace, so here it is. If you've not seen it, if you've seen it before, apologies. If you've not and you enjoy it, a loud groan of appreciation is the appropriate way to register it. I put this up because working in AI for the last decade or so has been a bit like living in a large Genie joke, except of course the butt of the joke is disproportionately distributed. So what we're going to do is remind ourselves how LLMs work. So what do LLMs do, large language models? They predict the next word. That's all they do. So given some set of words, they predict the next one. So the cat sat on the, your turn. Thank you. There we go. We got that one right. Good. What about this one? The quick brown fox jumped over the lazy. Yes, great. And then the next word might be, we'd see the quick brown fox jumped over the lazy, and in that context, dog. But actually, it might be something else. So what LLMs do, they don't just predict the next word, they give you a probability for all possible words that come next. Okay, so they are essentially just building huge statistical models of language. And they are predicting the next thing that comes, and they add one word at a time, so an approximation, and generate a large bunch of text. So let's do one that requires a little bit of memory of history. In 2023, President... Oh, nice. You saw where I was going. You fell into my trap, except. Right. So LLMs, large language models, are trained on usually large subsets of data that come from a thing called Common Crawl. And if that sounds like something that emerged from a swamp, it's about right. So these things are full of cultural biases. In fact, we share them, right? Humans have cultural biases. A huge amount of the data that the systems are trained on come out of the US, and in the US, the word president means the president of the US, and so we would expect Biden in 2023. But of course, globally, we have all sorts of diverse interests, and so there's much less, ends up being much less data talking about Macron, and that gets reflected in the likely words that a language model will use. So these things are giant quantities. They have many billions or trillions of parameters, and essentially they operate by muscle memory. So they don't have any kind of structured reasoning, or they don't remember, oh yes, I remember that article about Joe Biden and he was president in 2023, or I have no semantic memory that says, yes, these are the presidents of the US. these things are producing these words effectively from implicit muscle memory. They just instinctively know what the next word is going to be. And that's why you need all of these incredibly complex tools to interrogate language models to understand why they do what they do. Here is one that I don't want you to answer. And I hope you're feeling discomfort right now. But LLMs don't feel discomfort. They will just happily produce another word that follows onto this. And you can bet it will be a word that describes some protected class of people, either an ethnic group or a religious group or a political group. The language model has no concerns about just producing the next word, because that's what they do. So they have this huge repository of human bias that they're trained upon, and they faithfully reproduce it. That's because statistically the next word in all of my training material is group X. I will put group X next. So this is all by way of motivating the approach that my team are taking. I'm not as clever as these people. So instead of diving into these colossal models, what we're going to do actually is make the models much smaller. So this is a model of what happens with AI now. The bit on the left, if it's a student studying for exam, we call that studying. In AI, we call it training. So we expose our language model to a huge amount of text, trillions and trillions of words, and the model learns statistically what words follow what. Then when we ask it a question, it doesn't have access to that anymore. It's expected to memorize it effectively. It has an implicit memory. I'm a little bit careful. It's not faithfully memorizing the text, but it's formed a statistical model of the text. But in order to capture all of those complexities about who was president when, it needs a lot of model capacity. These things have billions or even trillions of parameters as a result. So what are we going to do? We're going to remove the closed book exam environment and replace it with an open book exam. So now the book, all of the knowledge is available to the language model as it's answering the question. Why would we want to do that? Well, we can move a huge amount of model capacity out of here and leave it in the book. All right, so now my brain can be much smaller. Maybe my brain can deal with basic grammar. It can construct coherent sentences. But a lot of the knowledge that we were requiring our systems to have before can now reside in a repository of text. Doesn't sound like we've gained very much, but actually we may have gained some useful things. Because what's happening now is that instead of remembering implicitly as a muscle memory who was president of whatever country in 2021, I can open the book and look it up and acquire that information on the fly. Why is this good? Well, actually the reason this is good is the reason that it is very expensive to train large language models. So, I mean, the companies don't release this data anymore, but a couple of years ago, was it GPT 3.5 or GPT 4, the cost of energy cost of training the model was the same as the energy cost of building and running 6 cars from go to O. Lifetime energy consumption of 6 motor vehicles, including construction, smelting the metals that go into them, the whole works. So this is not small, it's hundreds of millions of dollars, if not billions of dollars to train a modern model. If the model is trained on material that includes repugnant bias, and we want to get rid of it, then that's a challenge. And really the only way we can do it is to retrain the model, and nobody wants to do that. Or if it's trained on material that's copyright, and I exercise my right to that copyright, say, no, you're not allowed to train your model on that, you better go retrain, that's a problem. In the EU, I might exercise my right to be forgotten and require material to be removed from the training set from this, disinformation, etc. Conversely, if we have a curated list of knowledge, we can add it as we go. Because this book here, this is really like a database. So I can stick extra information into the database. No retraining, the model should update its behavior. So we want to be able to design our systems in that way. We have a project to do that. And we hope that it will enable these kinds of facilities. Thank you.
Is the microphone on? Let's just do a little 10 minutes and then we can go to lunch. I know everybody's tired and hungry. I just want to summarize while you're thinking of some thoughts. One is, Tom was telling us, instead of having this big muscle memory machine, make a small machine that can read the text like a rag store. And if you happen to be in Australia or Singapore or China or the US, you put the right text in there and it can read that and use that. Caren was saying it's not only text, it's multimedia. And you want to align the media appropriately so that you get the right information without misinterpreting, because you can compose the media. Sarah was saying sometimes you want to go inside the box and actually put statistical boundaries and certain kinds of mathematical limitations inside the machine, what it can and cannot do, what it can and cannot learn, so that you have certain kind of guarantees. And I was saying that when all is said and done and all this wonderful things has happened, AI is still going to make mistakes. And we are still going to say, why did you do this? And we will still want to have some kind of explanation to decide, are we going to kill that company? Are we going to find the machine? Is it a reasonable thing that everybody would have done? We want to have an explanation in the kinds of terms that we as humans accept. So this is 4 perspectives what AI people are busy doing to try to respond to the pressing kinds of questions that people like you raise and say, this thing is dangerous and it can hurt us. We need to figure out how to control it, how to avoid it, how to teach people to use it, etc. I think AI is doing its best. As you know, there's a lot of internal dissent within the AI community. People are fighting with one another about this. It's not just a bunch of few oligarchs making a lot of money. There's a lot of careful people who really want this to succeed, who do not want to go into another AI winter and a Luddite reaction. These kinds of responses are what you see. So are there any questions?